All right, so this is lecture 28. We're going to continue our discussion of standard model. As if there are any questions along the way, just ask. Um, the final exam, quote unquote, is going to be May 7th, I think, is the or 8th, I don't remember. The first Thursday of May, same time as the class. And for the four of you who are doing it, I'll send you a message and a Zoom. There will be the same Zoom link as the course. And we'll go over your homework. All right. Um, Standard particle physics. We said this is renormalizable, interacting four-dimensional quantum field theory. Strong nuclear force, electroweak is the gauge theory content of it. SU3 color times SU2 left times U1 hypercharge. There are 8 massless gauge bosons, gluons. There are 3, these are all spin 1. There are 3 W bosons and 1 B mu, which is the single spin 1 particle that is the carrier of the hypercharge. Of course, there's spontaneous symmetry breaking of SU2 times U1 down to U1 electromagnetism. We described this. The left-handed stuff coupled to left-handed fermions, and there are 3 generations of particles. We said that because this is a chiral gauge theory, there are no masses allowed for fermions, period. Of course, same for gauge bosons. All right. Then, so here's the matter content. There are leptons. These are the ones that do not participate in color interactions. So there's neutrinos, electron, muon, tau, nu m's. The m is the generation index. Em, electron, muon, tau, and so there's only one Majorana worth of neutrinos. They're the left-handed ones, right? And for the EMs, for the other leptons, you have left-handed and right-handed. So 2 Majorana worth of degrees of freedom. For quarks, you have up and down, same generations, up sharp top, down strange and bottom. They both have 2 Majoranas, left and right. So it's convenient and conventional to express everything in the representation theory of SU2 left because that's what's spontaneously broken. So putting muon left hand neutrino, which is only left-handed, and electron left-handed piece into a doublet, SU2 doublet. It's a lepton, SU2 lepton that is transforms in 2 of fundamental of SU2 and minus half is its hypercharge. The right-handed one, of course, doesn't see color or SU2, but it has hypercharge -1. All of them have hypercharge. So for quarks, we package again the left-handed up and down all the generations. This is the fundamental of SU2 left. That's what we were showing manifestly. But it's also fundamental of SU3. The hypercharge is 6. And for the right-handed U and D, this is a representation. Higgs is a complex scalar field that is coupled to SU2 left. Of course, we wanted so that we could break the spontaneous symmetry. We could spontaneously break the gauge group by giving a VEV to Higgs. So the gauge theory content of it looks like this. This is the Yang-Mills piece, of course. Then this is the kinetic term for the leptons and kinetic term for the quarks, right? So for the leptons, the representations are listed, and I'm not going to repeat this. We went over this a couple of times. Now, as I said, things to emphasize, all the fermions are massless unless we spontaneously break gauge invariance. For example, and the issue we explained pretty clearly that any mass term will necessarily couple the left-handed to right-handed guys, and that will not be a gauge invariant term for if your group is SU2 left. So There is a. We also mentioned there is a possibility of the CP violating terms just in pure kinetic term in gauge theory piece, and that is adding to the standard Yang-Mills a term, topological term that if in lecture 30 I might actually comment on this. Um, that's defined this way. This is the analog of E dot B in electromagnetism, but it's well defined for any uh, non-abelian gauge theory. Why do I call this topological? Anyone wants to take a guess? It's never been observed, by the way. The coefficients are have been experimentally measured to be zero. Why do I call this topological? Take a guess. Don't think too hard. Something they could check with everything you do know already.
So it's related to the curvature.
Um, yeah, but there is something simpler than that. If you vary the Lagrangian density, what do you get with respect to a field? You get the equation of motion, right? A term is one important feature of a topological term is that it should not contribute to an equation of motion, right? If it does contribute to the equation of motion, that's the local data, right? So it's visible, it's reflected in local data. It cannot contribute to that. So it could vary the action as we did before for the Yang-Mills piece and get the equations of motion, and you see immediately that it does not contribute. Good. So theta 3 is the one that we often discuss. This is the one corresponding to QCD, right? SU3. And there are bounds on how small it can be, phenomenological bounds, smaller than 10 to minus 9. And this is called the strong CP parameter, theta 3. All right. So looking at the Higgs coupling, so there's the kinetic term of the Higgs and the potential that, of course, spontaneous reactive symmetry. This was the potential. And then Higgs also allows for Yukawa type couplings to fermions, right? Leptons and quarks. This is very important. This is how mass is, how all the fermions get their masses, right? And the important part is that for the quantum numbers to add up properly, well, first, Higgs is a doublet under SU2, right? So it's transforms in two. You need your fermion. Any fermion that's supposed to get mass through spontaneous symmetry breaking by a web of Higgs should be transforming and should have a piece that's SU2 that's SU2 left charge. So neutrinos don't. Therefore, you can't write the term here. There's no Yukawa coupling for neutrinos here, right? So they don't acquire mass. They can't have a mass. And that's just obvious because there are no, as we said, mass requires a coupling of the left-handed to right-handed. There are no right-handed neutrinos. But now you also immediately see, yeah, well, actually, I said what I said. All right, so here's what you write. You see, so as I said, these Yukawa coupling that you write down need not be in general. These coefficients are general matrices, so they're not diagonal in generation, right? What we're gonna see is that we're gonna diagonalize these matrices so that why do we so what's the problem with this not being diagonal? The Vev of the Higgs will give mass to the fermion. What you find is that the kinetic term of these fermions are not going to be diagonal. That's not good. We always want the kinetic term to look canonical. So we're going to diagonalize these guys at the cost of a bunch of other interactions getting messed up. So what other interaction gets messed up? We're going to discuss that today. That's the coupling to W plus W minus, right? So the charge current coupling. And it is equivalent. So those are the only terms that get messed up. And those are the terms that are flavor changing, right? Flavor changing means you jump generation, you change generation, right? These matrices, when you diagonalize them, you have redefined your fields. We're going to do that in a second, right? in this new field definition, if a term gets messed up, like gets become non-diagonal, it means that it's flavor changing physics. Flavor is generation, right? All right. Spontaneous symmetry breaking, we said, is easier in unitary gauge. Then you set the top component of phi to 0, and then this is the vev of the vev of phi, and then the real function that fluctuates here is the real Higgs field. Unitary gauge is convenient because it eliminates the diagonal term. Sorry, eliminates the this off diagonal term, right? So the total Higgs action is like this. So this is just a kinetic term. There is a mass term. There is h cube and h4. Notice the structure of the couplings. They're all coming because these couplings are related to each, come from spontaneous symmetry breaking. They're all related this way. And then, so here's the Vev of the Higgs V, which was 246, I think. Uh, GeV. So it's very high scale. It's very, very high scale. Just for comparison, what's the mass of a proton? Yeah.
1 GeV, just shy.
1 GeV, right? That's the scale to have in mind. What's the mass of an electron?
Half a KeV.
Very good. I'm glad somebody. So there are these. These are good numbers to have. Like at least keep track of orders of magnitude, right? So what is LAC running at? Roughly speaking, 10 TeV, right? That order of scale, right? It's TeVs, right? So what is the scale that we just said that, right? The scale of spontaneous symmetry breaking, electroweak spontaneous symmetry breaking, is set by the Vev of the Higgs, right? As a quarter of a TeV, right? So we're operating, say, at 30, 40 times above that, right? Something that so we're generating a lot of particles, right? Okay, so not we, they are. Maybe you are. So there's V plus H. So the V piece is the thing that gives mass, and the H piece is the part that ends up being the coupling, right? If you do get a mass, it means that any particle that gets a mass also comes with interaction with Higgs, right? That there's no way around it. They all come packaged this way. So recall G2 is the strength of the SU2 left interaction, and G1 is the strength of the U1 hypercharge interaction. All right. Okay, so here's the W plus minus. Here is the Z boson, right? And then the Yukawa term are like this. The spectrum we discussed last time, I'm going to repeat very quickly. So we have a one spin zero particle. We're going to see that this is problematic. I'm going to tell you in advance. This is problematic in physics. Anyone wants to take a guess why? It's problematic. Why did I not start? Like we started teaching lambda phi 4, right? But we kind of abandoned that. I started talking gauge theories, blah, 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 right? Why did I not include? So what did we see? We saw that like when we had non-abelian gauge theory, right? It had anti-screening. Fermions had screening, and that was not good. But I said, okay, charged fermions are, if you have enough anti-screening, a little bit of charged fermions are tolerated, and that's what we use to build our theory, right? It's a similar game with charged scalar, right? But I never discussed charged scalar except for Higgs. Why is that? It's a tricky question. It's hard to answer. I'll comment on that. Also, another thing to know, just from the point of view of condensed matter, in QFT1, we said that low energy physics, a lot of it is emergent. You see QFT as an emergent thing deep in the infrared. Is just a phenomenological observation that we tend to not see scalars much in low energies. There's a good reason for that. Anyone wants to take a guess? All right. This is a problem called hierarchy problem. And we're going to actually see Stanomol suffers from it because it has a scalar field. All right. Spin-bound particles, they're the W bosons, right? That are massive this way, blah, blah, blah. We said that there's a remaining U1 electromagnetism that rotates W1 and W2 to each other. This is the gauge transformation. This is unbroken, and the corresponding charge, the electric charge, is T3 plus Y. Y is the hypercharge of the U1, right? If you have a U1 group, the hypercharge is just an integer. The charge is an integer. Well, sorry, is a number. Okay. This is the spontaneous symmetry breaking. We defined this theta angle. If you recall, we just took the combination G1 over square root G1 squared plus G2 squared, right? So this is G1 and G2, and the value of G1 and 2, whatever it is, right? You think of this, and then you talk in terms of this angle, right? So you talk about G2 and this angle, right? Um, okay. So there's a cosine and sine of that. The Z boson is this, the photon is this, the photon remains massless. It is due to the fact that you still have the abelian U1 electromagnetism gauge, residual gauge transformations that survive. There's a, and then, yeah, we saw that spontaneous symmetry breaking means that 1 degree of freedom of the scalar field was eaten, in a sense, by the W bosons and Z bosons and the required mass, right? All right. The spin half particle also, the spin half particles content of the theory. These are fermions that acquire mass through the Yukawa coupling. Now, as I said, to see the mass, we'll have to diagonalize these guys, right? So we diagonalize them. That there is the F, which is the, so this is the Vev of the Higgs. F is the matrix for coupling the Yukawa matrix for electrons. For up quarks is G, and H is for down quarks, right? All right, very good. So here, what I'm gonna do is I'm gonna diagonalize them. This is what we start with. This is the Yukawa coupling we start with, right? Now, apply some matrix linear transformation to E's, U's, and D's, right? Call these guys U of E, U of U, and U of D. Okay? Similarly, for the right-handed guys, apply V's. Good? These are field redefinitions. These are field redefinitions, meaning what? Where we take the electron and tau and redefine a new combination of them. Actually, so electron and tau are the new combinations, right? Because you always want your kinetic term to be diagonal. It's representation theoretic, right? Okay, so we're gonna choose in a second. You'll see. So any such field definition is allowed, but you want something that's not silly. We want something that simplifies your transfer, your Lagrangian density. So we're gonna pick V's and U's to be complex conjugates of each other. These are matrices, meaning the matrix element, but matrix element, they're complex conjugate of each other. Okay? All right. Why do we do that? The reason we do that is that, let's focus on this term. E undergoes the field redefinition using V, and curly E star undergoes the field redefinition under UE dagger. So what we end up with is UE dagger FVE. This is a matrix. Now, because U was V star, the dagger of that gives you V. F, these couplings are real matrices, right? So this is a similarity transformation. These guys, if they are diagonalizable, there exists a V transform that will make them diagonal. Good? All right. All right, in Dirac notation, this is what it is, and then we've used U and D, and this is the diagonal form of it. But this comes at a cost, as I said before. This comes at a cost that there will be terms in the Lagrangian that, under this Filter definition, will now change. The only terms that are of that type are couplings of this sort. So they have to have. So if you have a term that has up, look at our field definition. If it has up and down in it, right, it will get messed up. It should have a different combinations of these guys for it to get messed up, right? And the only such terms are these kind of couplings that appear in W plus and W minus. I'll come back to that. All right, good. So now we're gonna talk in this basis. For the most part, for a lot of what I'm going to say next, which is all about the gauge theory content of the theory, it won't matter. And then we'll get to these terms and discuss them. So this is about the coupling of the gauge field to the fermions. By the virtue of the fact that these terms are going to be now non-trivial and mixing, these are the only terms that are going to have flavor changing physics, right? All right. A quick set of comments. So G3, which is the coupling of SU3, becomes strong at 500 MeV, have a 500 MeV, which is much lower, right, than spontaneous symmetry working scale. At this scale, quarks and gluons are no longer in the spectrum. The theory confines, and we have color singlets, hadrons. And if the color singlet is made out of glue balls that we call gluons, we call it glue balls. If it's made out of quark antiquark, it's mesons, for example. Pions are such examples. And if there are three or more quarks, we call them baryons. Yeah.
The, the lightest baryon proton has a mass that's actually above that scale that G3 comes from.
Right.
So does that mean that like quarks are sort of already starting to become the degrees of freedom that matter at the point that you have a proton?
Yeah, this is a order of magnitude estimate, right? A factor of two or something like that are not necessarily very meaningful. Actually, wait a second. Um, 246. No, I don't have the what I was looking for here. Right. Sorry, I don't have it. Never mind. Okay. Thanks. Sorry. Any other questions? So another way of saying is that when you get to energy scales that is near the mass of proton, you're about the same scale that things are start falling apart, right? The proton cannot be stable. Of course, once you have enough, yeah. For the most part, most of the mass of the proton is the gluons. That is the interaction mass, right? That's a signature that's the theory is strongly coupled. All right. So the Higgs potential. There's a cubic term and then there's a quadratic term, right? But notice that, so these are the cubic and quadratic term. Notice that they are correlated, they're written this way. I said the coupling of anything, any particle to the Higgs is going to be the mass over the VEV. That's the strength of the coupling, right? So for the case of Higgs, you see that explicitly, right? So the Higgs gauge boson is like this. there's the yeah. So this is um, there's W plus W minus coupling to Higgs. So there are um, these kind of things, right? This is one, and then there. This was this one I drew, and then the other one is right. And similarly, you have oops this right. So those are the four terms that you see here. You also have fermion Higgs, which is universally the coupling is described this way: mass of the fermion over the vev of the Higgs. So that's uh oops, sorry. That's like this. All right. As I said, all particles are coupled to Higgs. The coupling is proportional to m over v. V is 204 G 46 GeV. So all the particles that we have on the table of masses are much lower than 246 GeV in mass. That means that they're weakly coupled, except that one that is kind of gets sketchy, and that top quark, which is 173, right? So top quark has 173. It means that, oops, sorry. This infraction term, right? It doesn't really suffer much suppression. The coefficient that comes with every vertex like this is not very small. So in perturbation theory, it's not very reliable. But because they are very very low energy, they're very very heavy. You don't expect to generate a lot of them unless you go over TVs and like in at CERN we're operating near like 10 something TV and we're generating a zoo of lots of these guys. So there will be tons of top quarks. What did I say? 173. Okay, this table says something else. Um, Wikipedia. Maybe I'm wrong. I'm probably wrong.
Latest combination was 172.5.
172.5. Oh, I'm closer than Wikipedia. Ah, wow.
Or the combination was 173.
Okay.
Updated.
Okay.
Just a year and a half ago.
All right.
So
I'm not sure if this is Wikipedia. It's somewhere. I don't remember where. But like notice here there are things to pay attention to, right? So look at the mass of the quarks, right? 4.6 4.8 MeV, right? 1 GeV for sharp. The gap between these masses are enormous, right? This is of the order of 1 MeV. This is of the order of a GeV, 1,000 times. So you go to second generation, this is 1,000 times heavier. This is 200 times heavier. So not nearly as big. Then from here to here is another factor of 100, right? 100. That's enormous amount, 2 orders of magnitude, right? But from here to here is not nearly as much again. The neutrinos, you see some masses here. That is something we're going to mention later. So half MeV is electron. That is pretty darn light, right? Just compare this. And then muon is 300 times heavy, 200 times heavier. And then tau is how much more? 10 times, actually. All right. Now, the masses of these guys are of the order of 100 GeVs. They're below 100 GeVs, right? So they are not, of course, they're not too far off from the Higgs mass, right? So when W, the coupling of these guys to Higgs is going to be controlled by, say, 90 over 246, which is not a very large or small parameter. All right. Let's talk about the self-coupling of the gauge boson. We're gonna have W plus minus Z and A mu photon. So the field strength associated with them is going to be, we're going to call this F mu nu, right? This is the F mu nu of electromagnetism. We're going to call this Z mu nu and then W mu nu plus minus. These are the field strength. There will be cubic terms and quadratic terms. Do you expect what do you expect? Where do field strength appear in the cubic terms or the quadratic terms? Why? Oh, these are cubic terms I'm showing. Quadratic terms I haven't shown yet. But quadratic or cubic? Where do they come from? First, let's describe where do these guys come from. Just what's the action? The action is this, right? Now, what you have is covariant derivatives for each of these guys, right? So let's say W, right? Mu A. There's a covariant derivative. The covariant derivative in it has del mu, right? And then the next term is gonna have the corresponding gauge field. Like so W mu TA or something. Good. When you expand this, there are four terms. When you get the quartic interaction, there are four terms. It means that there are no derivatives, right? All of them should come from this term. If you want a four-body interaction of them, four of them. Is it clear what I'm saying? Right? No. So there is this guy acting on W, right? What is going to happen? This is just the first term. There is going to be one term with W and then the other term with two W's. You have two such combinations. When you expand this, you're going to get a standard kinetic looking term. You're going to get a term that's like W4. It has no derivatives, right? So quartic term does not have derivatives. The derivatives will be in the cubic term. But to get anything like field strength, you need a derivative. So the field strength will have to come from the cubic term, not the quartic term, right? So here it is. The rest is algebra. You just write down the quartic term. It's pretty straightforward. Just a couple of lines of algebra. The quartic terms look like this. IG2 sine theta W. IG2 cosine theta W. So just recall what these were, right? This is related to the relative strength of G1 and G2. Every time you have a mu photon, it comes with a sine, and every time you have Z, it comes with a cosine. Keep that in mind, right? So you're gonna have the W mu. This is the field strength for W boson plus. Will have to come with W minus, right? And then A mu. So what is this? This is like this kind of vertex. This is the kind of vertex. This is A mu, right? W plus, W minus, but then you do know there is a derivative here, right? So in the momentum space, there will be a P associated with this guy, right? The derivative terms come with a momentum. There's a Z, so there, sorry, there, this is, so this is the term that describes the coupling of the gauge W's with gamma are these. Good. So W acting on the photon, W acting on W minus, W acting on W plus. Then omega WW, sorry, WWZ is basically same structure with its corresponding field strength. So W plus and minus are called charged current, and Z is called neutral current. Do you have a guess why? I'm going to say in a bit. You want to say it?
Interactions with W carry charge.
Electric charge. Right. So this is from the point of view of electric charge. All right. The quartic terms. Quartic terms, yeah. So there is the interaction of four W's. Here's what it looks like. There's interaction of two W's and ZZ's. So four W's, the only thing that matters is G2, right? Now, ZZ, if you have two Z's, every Z comes with a cosine theta, right? Because we did a rotation to define Z and uh, Z, right? There is WW photon, photon, gamma, gamma. There are A mu, A nu. And these guys again come with signs, right? And then there is ZA terms that come with sine, cosine, right? Good. G2 sine theta is the thing that comes with every photon. That for that reason, that should be identified as electric charge. This is the electromagnetic charge of a particle plus one. All the interactions I've described so far here, right? Quartic, quadratic, they preserve C, P, and T separately. Good. Charge, parity, and time. Now, let's talk about charge current fermion interactions. So what are these terms coming from? Where do these terms come from? From the covariant derivative pieces in the kinetic part, right? Left-handed leptons, right-handed leptons, left-handed quarks, right-handed quarks, the kinetic terms, right? So here's what they look like. This is the D slash is the covariant derivative and their gamma matrices, right? This is what it looks like. The covariant derivative here, because things for the left hand, the ones that are coupled to SU2 left, right? I'm gonna focus on these. So first, take this term. This is neutrino up, electron, neutrino bar, electron bar, right? And this is the coupling in the middle. So notice that the off diagonal terms here will be flavor changing, right? The off diagonal terms here will take an electron and turn it into a neutrino, right? Whereas the diagonal guys will be electron, electron, neutrino, neutrino. That's a flavor changing physics. I think I said generation changing before. That was a mistake. Flavor changing, right? So I'm gonna focus on that in a second. But importantly, the off diagonals are W mu plus minus, right? Z and A go into these combinations. That is why the only flavor changing physics that there is through W's. Right? And then these terms are gonna, well, sorry, these terms are just gonna look like this. Nothing fancy here. They don't couple to, these guys do not couple to SU2 left. So all that you see is B mu, which is the U1 hypercharge. All right. So good. So this is a structure we have. Now, see what happens. So let's take, for example, the neutrino. Okay, so take this term, neutrino, and W plus an electron, right? This guy. So one of the off diagonal terms. Good. And then take the other guy, which is W minus electron neutrino. So these are the things that flavor changing. For the leptons, for the quarks, it will be again W plus and minus up and down. So you send up to down and down to up. But we didn't need diagonalization diagonal matrices for nu and electron. When we diagonalize their mass terms, there were no u. So what did we do? So each electrons came with u's, right? The left hand, let me show you. Electrons came with u's. Here they sit next to neutrinos, but neutrinos we didn't have to diagonalize. There was no mass, so that is not an issue here. But up, we use u's for, and this guy we use u, and the other guy we use v on the other side. So let's look at the term again. Where was it? These d's, one of them is, so yeah, this is up and down. So what you're gonna have is u dagger. Sorry, I misspoke again. So one of them is u, the other one is ud, right? Dagger ud. So this is a matrix. It's a unitary matrix, right? And we're gonna call them VMN. And I apologize that I already called something else V. V was U star, right? So here we end up with these things that are not diagonal in generation. These are called the CKM matrix. This is a CKM matrix. It's Kebibo Kobayashi Masakawa. Probably, I'm probably wrong. It's so CKM matrix. Good. This is the only place where there is a consequence to our diagonalization of kinetic term. Good. Questions? So these are the CKM matrices. This is a CKM matrix. CKM matrix because it's a U dagger U. And these were coordinate, these are field redefinitions. These end up being a unitary matrix. It's convenient to parameterize it this way. So the matrix, we're going to parameterize it this way. If these are sine and cosine, means rotation. Oh, sorry. My bad. IJ, IJ. So these mean sines and cosines. So then what is this? This is just a rotation. What is this? This is just a rotation. If delta 1, 3 was 0, this is another rotation. If delta 1, 3 were 0, these were all rotations. The matrix will be a rotation matrix in 3 dimensions. It's an actually Euler angle. It's like a general, this is like the composition into Euler angles, right? A general rotation. But because of this delta 1, 3, the matrix need not be real. Good? So here are the observed values of it from 2008. So I'm a little bit outdated. The angles of the CKM matrix, 1, 2, so these are generations, right? These are generations. So the angles are about generations, right? The mixing angle of generation 1, 2 is 13 degrees. All right? The mixing angle for generation 1, 3 is 0.2 degrees, and 2, 3 is 2.3. Why are these numbers, some of them are so small? We don't know. There's no understanding of it. 0.2 is a very small angle. And so is 2 degrees. Now, this delta 1, 3 is 68 degrees. This is not small. So theta 1, oh, wait. Did I make a mistake? Yeah, no, that's right. Theta 1, 3 is much smaller than theta 2, 3, much smaller than theta 1, 2. Well, this is a factor of 10 in here, much smaller than 1. There's a factor of 10 in here. There's a factor of 10 in here, right? 10, 10. Yeah, it's 10 between all of them, right? So one order of magnitude. There's no known reason for this. So this often is the interpretation of this is that fermion flavor changing physics is suppressed. Okay. Interestingly, if CKM matrix were real, if that delta angle, this angle, right, was sorry, this angle was either 0 degrees or 180 degrees, right? It would have been real. Pi, right? If it were real, you could check that CP would have been a symmetry of Standard model. But CP is not a symmetry when CKM matrix is not real. So this is a source of a CP violation. Because so now here's the thing. This is sort of a problem now. What is the problem? You might have said that the reason, remember there was another source of CP violation. It was um, this topological term we could have added to the non-abelian gauge theory, right? If all the other terms in the Standard model and the coefficient of which was 0, phenomenologically, it's observed to be, we have never seen this term, right? If this CKM matrix were real, then you would have said that, oh, all the other terms respect symmetry. Therefore, this has to be absent because of a symmetry principle. Right? It's a symmetry of nature. But now that the CKM matrix, that delta 1, 3, is not real, CP is not really a symmetry of nature, there's no reason not to include it. Right? Is that logic clear? Because you write down all the terms consistent with a set of symmetries. If that symmetry already you have observed a term that violates a quote unquote symmetry or transformation, then you should include all of them. Right? There's no CKM matrix for leptons. Hopefully that's clear. Right? It had to do with the fact that neutrinos didn't have a mass and there's no corresponding diagonalization principle for it. The fact that there's no CKM matrix for lepton, it means that lepton W boson interactions are universally just controlled with G2. There's no other data that goes into it. All right, questions. How am I doing on time? I think I'm doing all right. Questions? This is called weak universality, by the way. All right. So this was the charge. This was the hardest part of the story, most complex part of the story. The neutral current fermion interaction. So we just described the charge current, W plus minus, how they couple to other things, to fermions. Now we're going to describe the neutral currents, which is like A mu and Z mu coupling to fermions. So recall what Z mu and A mu were. There was just some sort of rotation of W mu and B mu, and these angles were related to the relative strength of G1 and G2. So the neutral current is a sum over fermions. All the fermions take the following form. The Z mu part of it is basically fermion bar, this thing F, right? This is what sits in the middle. And yeah, there are these two terms. That's the structure of it. You just need to expand and see. For the coupling to A mu, this is the form it takes. Good. All of this is coming from the expansion of the kinetic term for the fermion that include a covariant derivative. Right? Now, To organize things better, so this is pretty intuitive, right? A mu, gamma mu, fermion bar, fermion charge of the fermion, i.e. sum over F. This is completely intuitive. To make this other term intuitive, it's convenient to define the following couplings. So 1/2 T3 minus Q sine W squared, we're going to call that GV, and half T3, we're going to call that GA. So the fermions coupling to Z mu takes this form. There's no flavor changing physics here. Electromagnetic interactions, as opposed to so these electromagnetic interactions preserve C, P, and T separately. The neutral current interactions violate C and P, but they preserve CP or T. Right? So what we saw was that the most offensive term was this charged current to fermions that was CP, sorry, the CKM matrix that led to CP violation, right? So CPT is a symmetry, we know that. There's a proof of that for all quantum field theory. It could have been that CP is a symmetry as well, but it's not. Even though the neutral current term, neutral current and all the other terms, except for that flavor changing physics, respected, right? It's not a symmetry. All right. I guess this is a table of what uh, Q and T3 are and GV and GA. Questions? Yeah.
That'd be wrong. Exotic and also CP violation was usually noticed. Or was that just parity violation?
There's no CP violation within standard model. That's important. Standard model, right? There are generalizations of it for that we're going to talk about now. Well, I'm going to mention in passing. Okay. Exactly. Next slide. All right. Any questions about the standard model so far? It's a very nice theory. It's been enormously or tremendously successful in recent in predicting or matching, predicting and matching the data. But then it's got some theorist problems. Theorists are some are theorists and some experimental theoreticals and some experimental problems, right? What are they? Well, it explains a lot of things, but it doesn't explain everything. Of course, it was designed, you can't expect it to explain something that's not designed for. In the formalism, there is no gravity. Just forget about it. So it can, that cannot be a problem, right? It's not designed to do that. But we do know there is dark matter. Dark matter is, we do know gravitationally, and there are many different ways of different reasons we believe that the mass energy in the universe, 5% of it is standard model particles, 26% of it is not standard model particles, but this is conventional matter. Conventional means it has to be particles of sort. Or another way of saying it is that, well, you guys haven't learned, well, I don't want to, it whatever it is, its response is like space time. It behaves like, sorry, it's space, it behaves like matter. It behaves like particles. We don't know what it is. We have absolutely no clue. And whoever told you they know, don't believe them. We don't know what dark matter is, but we do know 26% of the mass in the universe is dark matter. And standard model cannot explain that. Only 5% of the matter out there is standard model particles. So what's the other 70%? That's dark energy. It's a source of something that we think lies well beyond standard model of particle physics, and we think it well, actually, there are many reasons to believe it's called dark energy because we do know it behaves very differently from matter. Um, for yeah, I don't want to comment more on that. It's not a course on quantum gravity, but I'm happy to tell you guys offline about it. So that's one thing, right? A minor thing. We're only describing um, 1/6 of the matter content. All right, that's fine. But we've never seen the other particles. So, but within the same set of particles that we're describing, we have some other issues. We observe neutrino oscillations, meaning in the sun, neutrinos are produced in the sun, for instance, or well, let's just talk about the sun, neutrinos produced in the sun. And we do know as they travel along the way to get to us, the neutrinos change their type. So there's neutrino electron, muon, and tau. Neutrino oscillations tell you that they're just changing as they go. What does that mean? It means that the kinetic term is not diagonal. That could be explained if neutrinos had tiny mass. And the mass that's coded for neutrinos often on these tables. So if you look at neutrinos, there are masses here. Uh, well, these are all upper bounds, right? They are deduced from neutrino oscillation. It's plausible, just like plausible, some other completely exotic framework keeps them massless and explains neutrino oscillation, although we don't think that's true. So that's another thing. All right. A very important other thing is matter antimatter symmetry. There is way more matter than antimatter in nature, and this is called baryon asymmetry. All right. I want to make the following distinction. Standard model of particle physics describes interactions. Good. It does not describe the state. The Lagrangian does not describe the state. It tells you applied to some crazy energy density, some soup of electrons and protons and whatever. It will describe the interactions and time evolution of that. Applied to vacuum, boring vacuum, it will describe it. These are ethical MAs of the physics. State is about what is your initial configuration that you're going to evolve with ethical MA. Now, good. Having said that, there is one little caveat. We in standard model particle physics we used one little bit of state, and that was the VEV of the Higgs. Right? When we gave Higgs a VEV, it is equivalent to saying that as far as Higgs goes, everywhere I have a condensate. Everything that travels through space is going through this condensate of Higgs. Right? That's one bit of thing that we assumed about Higgs, about the state. But the rest of it, as in the state that we live in, there could be all sorts of, it could be populated with all sorts of, a bunch of electrons and protons and positrons, all sorts of things. But when we look around, we barely see any antimatter. It's almost all matter. Why? That's just a fact. Now, some might argue a theory is not designed to explain the state you're given. It's not the task of the theory. The theory is designed to come up with ethical MA that involves an initial state. But think about the following fact that your laws of equations of motion of ethical MA are just fine, but somebody comes up with some crazy asymmetric state, right? And let's just say that's what you're given and evolve it. It might raise an eyebrow, like why that? A lot of problems with standard model of this flavor. The theory as a whole is not necessarily problematic. It's just some it's a little bit. Uh, these are theoretical problems, right? We would like to explain this, but it's not a problem for the theory per se. When I was a graduate student, or even up until quite a couple of years ago, so there's the set of arguments that are used to explain this. It's called anthropic arguments. I don't know if you. So this, to my generation, had the word anthropic had a different meaning. It was not a company. It was a set of arguments used in physics. Now things changed since a bunch of string theorists got together and founded anthropic. But all right, so here it is. This is standard model of particle physics. I guess this is the chart. You could look at them. And here is the summary of all these angles and stuff. Now, I want to point out a bunch of things. There are other problems with standard model. Oh, I think I removed a bunch of slides. There are other problems with standard model. Yeah, I completely got rid of. I was gonna say. Oh, I'm just gonna comment about this. Um, so I said earlier today that scalar field is a little bit of a problem. I think I'll say this actually. Wait a second. Maybe I have it at the beginning of the next lecture. I think I do. Oh, I've gotten rid of it completely. Yeah. So there's neutrino masses, dark matter, baryon asymmetry, strong CP problem, and hierarchy problem are the problems, but I'm not comment. I got rid of hierarchy problem completely. Let me say it in words. So recall lambda phi 4 theory. Lambda phi 4 theory. So Higgs, an important feature of Higgs that is that when we wrote down the Lagrangian, Lorentz Lagrangian for it, we saw that there was a term that had H cube and H 4. We didn't quite work with terms with H cube, but we did consider lambda phi 4 theories. So then there's the H2 term, and then there's a mass. Good. All right. Every time you see things like this is a mass. This is a mass. This is the mass at what scale? That's a legitimate question, right? You have to do renormalized perturbation theory, right? This is the mass that is set deep in the infrared around the scale of electroweak symmetry breaking or lower. What? And I call this deep in the infrared. Notice that. Why? There is a little bit of a problem. Lambda phi 4 had a feature which is as you consider one loop correction to a mass, this diagram appears. What did this diagram do? It increased the mass, right? Mass was a relevant deformation. You go towards the infrared, it grows. So standard model of particle physics has a cutoff, supposedly at some scale, very, very high. Things fall apart. Take that to be, I don't know, 10 to 16 GeV, Planck scale. 10 to 19, 18, 19 GeV actually. Or something somewhere around there. Just keep it large enough. Now down here at 10 to at electroweak symmetry breaking about 100 GeV, 200 something GeV, right? The mass of Higgs is what it is. This means that deep in the UV or UV theory, so this is a relevant deformation. Nothing protects this mass. All the standard model of particle physics, they got their mass through Higgs. So there's no worry about where the mass came from. But this guy, we put the mass of this in a sense by hand, right? And this mass must have been teeny tiny, fine tuned to be very, very small at the UV scale so that when it grows, it becomes this much, right? That's a fine tuning problem. This is a problem with scalar fields in general. When you add scalar fields in the infrared with some mass, because mass is always a relevant deformation, it makes no sense to keep the mass small. Mass has to be always large, right? Because whatever you include in the UV is just going to keep growing. Is that clear? Okay. That's one aspect of it, but there are many other things. Oh, another thing. So I think I got rid of the exact RG lecture, right? This year. Notice something funny here. So all these masses that are coded for these particles, they have the renormalization scheme in front of them, right? The ones that are messier calculations, they have the renormalization scheme. What does that mean? I said that we saw that in the first order perturbation, in the normalized perturbation theory, the first order, mass and those things were scheme independent. Scheme is the regulator, right? Choice of regulator. It turns out I got rid of exact RG, but that's just a feature of the physics in the vicinity of the fixed point. When the theory is perturbative to the first order, things remain to the first order. There is a notion of mass that is regulator independent. Non-perturbatively, when you discuss something like exact RG, mass and all of these things become regulator dependent. Because non-perturbatively, there is some physics associated with the regulator. Something actually happens here, right? All right. Any questions? So, the next lecture is going to be about because it's going to be about anomaly cancellation, chiral anomaly cancellation in Stano model. It's a chiral gauge theory, so for it to make sense, it must be that anomaly cancels. We're going to do that calculation and see that it actually does cancel. So the theory makes sense. We're good to go. The next lecture, next Thursday, is the last lecture, and if you don't have very strong opinions on what I cover in that lecture, there's a list of options on the website. Let me know. Otherwise, I'm just gonna do special topics and gauge theories. Questions? Not. Thank you, guys.
Thank you, that's it.
Thank you.